The struct on the left is nearly 40% bigger than the one on the right. And on my machine, code working with left structs runs nearly 70% slower, despite them both holding the exact same data. The only difference is the order that we declare the fields. Some recent languages, like Rust and Zig, have a feature where the compiler may reorder these fields to turn the left version into the right version. On the surface, this may sound like a harmless, free optimization, but in reality, it's a feature that often does more harm than good and doesn't actually help for the cases where it matters most. You may have heard that reordering struct fields is a free way for the compiler to trivially optimize your data, but that's not exactly true. Still, there are some cases where it really does help, so let's get into the details. You see, due to field alignment, some ordering of struct fields cause the struct to be larger than others. In a case like this, the struct is 12 bytes, because floats have a 4-byte alignment requirement, meaning that floats must exist at an address that's a multiple of 4. If you place the booleans after the float, you wind up with a smaller struct, since booleans have a 1-byte alignment requirement, and this pattern always holds. By sorting the fields from largest to smallest, you can guarantee that it will have its minimum possible size. The maximum possible size comes from interweaving big and small types. So, what's the benefit of getting the minimum possible size? If you set less memory usage, you're on the right track, but that's not actually super important. If you have millions or billions of instances of some type, then it probably is worth making that struct as small as possible. But for most cases, it's better to optimize for performance, which is the real goal of struct field reordering. While memory may be fast to humans, it's very slow for the CPU. To make that process a few hundred times faster, every time you read from main memory, RAM, your CPU will also read the 64 bytes surrounding the memory you read, and pull that into a cache. The size of 64 bytes is determined by the size of the cache line, which is the hardware that actually pulls that memory into the cache. So, the main goal of minimizing a struct size is usually to try and make it fit inside of one cache line. Looking at the example from the start, we can see that the larger version is 80 bytes, which means we can't fit the whole thing in one read. When we reorder the fields, we get it down to 48 bytes, so the entire thing can sit in the cache at once. So, what if the struct can't fit in a cache line no matter what you do? Well, that means that if you want to read the entire struct, you're forced to do multiple memory accesses. In reality, though, you don't usually need to read the entire struct. And that's what really gets to the meat of this problem. You, the programmer, are the only one who can properly determine which fields belong where, based on which fields are read together. Here's some sample C code. Don't worry about the specifics. There's only one thing here that really matters. Notice effect durations and active effects. The effect durations field is really large. Duration is a 64-bit integer, and we have 16 different effects, so that one field is around a kilobyte of memory. Obviously, it should be placed near the top of the struct, right? And we also have a 16-bit integer representing which effects are active. It's used as a bit set, so each bit represents whether that corresponding effect is active. With the supposedly correct field ordering, these fields wind up on totally opposite ends of our struct. However, it's unlikely that we would ever want to use our effects array without also checking which effects are active. That's why, in reality, we should be putting our active effects field right next to the effects array. When actually working with this data, the sorted version came out nearly 20% slower. Hopefully, that example demonstrated the problem pretty well, but what can be done? I admitted that in the case of a struct small enough to fit within a cache line, size is the right thing to optimize for. So, what if the reorderer simply stopped reordering once the struct was too large? Well, I would consider that to be worse than useless. It removes the guarantees in some cases, while still dumping that responsibility onto the programmer for the majority of cases. There are other cases where reordering gets in the way too. Let's say you want to read in a WAV file. They have a large, structured header, so you could, assuming your language's semantics allow it, represent that header as one struct and load the file's bytes directly into it. That way, you don't have to deal with pulling out each value individually, and you can conveniently validate the file and read out info using a familiar syntax. Of course, if the compiler reordered your struct, you'd lose the ability to do that. That's why every language that has field reordering also has a way to opt out with some attribute or keyword. My final and most realistic example of where this goes wrong is interfacing with other libraries. Indeed, this is the time where you will always see a keyword or attribute to disable field reordering. If I want my code to interface with a C library, which is a requirement for basically every program at some level via the OS, I can't have my program reordering the fields of the structs I give to C, since C has no way to know that everything got mixed up. One option you may be thinking of is to have an explicit opt-in attribute for field reordering, saying, I want this to be faster, but I don't want to do it myself. That may work in some cases, but I feel that it would be overused and make code worse in most cases. Plus, a lot of people would just not use it, and that leads me into my final point. The unfortunate reality is that most programmers just don't care if their code is 20 or even 100% slower than it needs to be, since computers are so fast. These days, so many people are using languages like Java, JavaScript, and Python, where almost all data lives behind pointers anyway. That is the sort of thing that just doesn't affect most programs. While it's nice to be able to gloat that your language is smart enough to optimize struct fields, most people won't notice the difference, and the people out there who actually do care won't be satisfied with your mediocre default. Furthermore, there's plenty of other good ways to optimize memory usage. You don't actually wind up with structs with more than an 8-byte alignment all that often, so the savings are often pretty small. The reason is that a struct alignment, under default C semantics, is the largest alignment of its fields, not the sum. In the worst case scenario, constantly alternating 8-byte line types and 1-byte types, you're still only wasting 7 bytes per field, and you'd save more by doing things like replacing 64-bit pointers with 32 or 16-bit indices, or making use of bit fields or bit sets, as well as being conscious of the backing types of your enums and choosing to use smaller integers where applicable. Plus, if raw bytes is your only metric, you can just pack the struct and ignore alignment entirely. Most modern languages make this pretty trivial, although there is a performance hit. All in all, it's just more trouble than it's worth. Maybe one day we'll get a compiler that can scan your whole codebase and heuristically figure out what fields are used together most often, but that sounds like even more trouble to me. I prefer languages that are clean and simple, with no fuss about trying to act smart, and field reordering is just that, trying to act smart. So, to anyone developing a compiler, don't waste your time writing that reordering logic, and don't waste your users' time calculating it for every single struct. That's all for this video. Leave a like if you enjoyed, and subscribe if you want to see more. I've been trying to get back into making videos faster and more often, so let me know if you have any more ideas in the comments. That's all for now, and I'll see you next time.